So from all this conversation we've had, there are two kinds of errors that we can envision. Now you have a null hypothesis, now you have an alternative hypothesis. In actual fact, there are two things that can happen. Your null hypothesis can actually be true, or your null hypothesis might not be true. So for instance, in our example, it might be true that there is no difference between physicians and non-physicians in this class. They are equal in number. In that which case, null hypothesis is true. But null hypothesis might not be true. It might be that there are more physicians than non-physicians, or there are more non-physicians than there are physicians. In that situation, when you so let's just know the first thing is that the null hypothesis can be true, and the null hypothesis might not be true. But what we're trying to figure out is that should we reject the null hypothesis or should we not reject the null hypothesis? So the first kind of error is the error of failing to reject the null hypothesis. So failing to reject the null hypothesis when in fact the null hypothesis is rejecting the null hypothesis when in fact the null hypothesis is true. So say for instance now, the null hypothesis in our theory is that physicians are equal to non-physicians in this class. There's no difference. That's null hypothesis, right? Now, if you conduct your study and you now say, oh, I found evidence that the null hypothesis is not true, so physicians are actually more than non-physicians. Whereas when you look at the actual population, when we look at it, there are exactly 400 physicians and 400 non-physicians in the class, which means that the null hypothesis is actually true, actually holds true in the target population when you look, if we had access to that target population. But when you do your sample, you compute a statistic, you do your p-testing, you find out that what you arrive at is that the null hypothesis, is that you reject the null hypothesis. That is what we call a type 1 error, which is essentially a false positive error. You are saying that your alternative hypothesis, you are saying that now you are rejecting the null hypothesis, you have actually found a genuine finding that physicians are more than non-physicians in this class, when in fact, that finding is not genuine when you look at the total population. That's a type 1 error. It's a false positive. Now, so that error, your alpha is actually how much of that error you are willing to live with. Meaning that, how much of the chance that I am wrong am I willing to live with? So if the chances that I would declare that I found a difference, when in fact there's actually no difference in the population, if the chance is 5%, okay, I will leave my alpha at 0.05. But if the consequence of making a wrong decision is so significant, somebody might die, something significant might happen, then maybe I cannot even tolerate any error. Maybe my alpha will be 0.001. So an alpha is actually an indication of how much of the type 1 error you are willing to tolerate. Now, type 2 error is when in fact the null hypothesis is not true, but you fail to reject it. Meaning that in the actual class, in the actual population, there are more physicians than non-physicians. There are like 500 physicians and 300 non-physicians. But after you collect your sample, you process your statistic, and you compute your p-value, your p-value is higher than your alpha. You cannot reject your null hypothesis. When in fact in the actual population, you should have rejected in the actual population, there is a real finding to be made. That is when that's a type 2 error. And the probability that of a type 2 error is what we call the beta, which is that the probability that you would fail to find a finding, to find a result, you fail to reject the null hypothesis, when in fact you should have found one, because in the actual population, that result exists. In the actual population, the null hypothesis does not hold. But yet, due to some element of chance, due to elements of chance in your sample, in the way you process your statistic, you are not finding that difference. Now, we'll move on from type 1 error because we've talked about alpha and we've talked about p-values. But type 2 error, a lot of time, remember that when we talked about our sample, we said if you randomly select your sample, the bigger your sample, the higher the chance that your statistic would actually represent what is the general population. So statistics have been able to show that sometimes the bigger your sample, the smaller the chance that you would not find a relationship when the relationship actually exists in your population. If you have 800 people in your class, for instance, if you are sampling just 10 people to figure out whether they're more physicians or not, things can fluctuate so much that you might not find a difference when in fact there's a difference. But when you have a larger sample size, it is likely, it reduces your beta, the probability that you would not find a difference when in fact a difference does exist, which is your type 2 error. So that's why you hear a lot about, well, do you have enough power in your study? And that's why sometimes people want to collect, people are looking to find, a very large sample size. Yes. But there are also statistics who have shown that, the more your sample increases, the lesser your chance of failing to find your finding when a finding does in fact exist in the population. But that does not mean that all the time, just go and find all the 800 people when you cannot find them. So sometimes for people, so usually it's a good practice in statistics, we say, why don't you conduct a power analysis? Meaning that before you start collecting for your study, why don't you try to figure out how many people you would need such that you would have a good chance of finding of discovering a finding if that finding actually exists in your population. But the question is, what is the good chance? The good chance depends on how much of error, how much of beta you are willing to tolerate. So maybe, okay, I am interested in, say, I need to have at least 80% chance of discovering the difference between physicians and non-physicians in this class, if that difference does in fact exist. Well, there's a number of people, there's a sample size that there's a number of people that you need to recruit if you want your chance to be up to 80% of discovering that finding. Meaning that your beta, that is the chance of not discovering your finding when the finding does in fact exist, would be 20%. If you can tolerate a beta of up to 40%, meaning that your power is just about 60%, you probably need fewer people. In essence, what I would just like us to understand though, is that even though many people just think about power in terms of the sample size and the error you're willing to tolerate, there are other things that kind of factor into whether you would actually discover that finding when it does really exist. Some of that, apart from sample size that we have talked about, and power that we've just talked about, the other thing is the significance level in the statistical test you're looking at. For instance, if you're willing to tolerate a lot of error in missing, if you're willing to tolerate a lot of error in concluding that you have found a finding when in fact that finding does not exist, a lot of error in actually rejecting the null hypothesis when you should not have rejected it, you might need fewer people. In essence, what I'm trying to tell you here is that the significance, the statistical power, the sample size, and the effect size all depend on one another. If one changes, the other one changes. If your alpha changes, the sample size that you need it changes your sample size. If your sample size is fixed and your alpha changes, it changes your power. And the relationship is that the power is your power is the probability that you would actually discover a finding if the finding exists. The more people you have, the more your power increases. The more the difference that actually exists in the population, that's what we call the effect size. So, for instance, in the population, in the actual population, say in our class, if actually in the full class, there are 700 physicians and just 100 non-physicians. So the effect size, meaning that the difference between physicians and non-physicians, is so large, it is much easier to discover that kind of effect. You might not need so many people in your sample. But where the effects, where physicians are almost equal to non-physicians, they are like just 390, 410, then the margin of error, the effect size is so small, the margin of error that you have is so low. So you might need more people. And the power, given the same number of people that you have, given the same level of significance, the power that you will have to discover a difference in that kind of situation would be much lower than the power you would have had if the difference was very wide. Meaning that when effect size is smaller, your power becomes smaller. The chance that you've made a mistake of not discovering that difference is higher, meaning that your beta is higher, your power is lower for the same sample size. So it's a jigsaw puzzle. You need to think about all four of them are related. When you change one, others, when you change one and you keep the others, when you change one and you keep the others constant, you change one and keep two constant, the fourth one changes. And a higher effect size means more power, lower beta. A higher sample size means more power, lower beta. But the higher significance means less power and higher beta. So poll 5. So I'm just gonna give us a few minutes to look at. Dr. B, are you still here?
I'm here. I'm just wondering, given how much we're behind time, perhaps you could just walk through the poll and respond.
Okay.
And then
That's a good suggestion. So here, you want to compare the average voting time ANC, rural areas versus urban areas for a minimal average difference of 20 minutes. So using alpha of 4.05, beta of 20%, you estimate that you need to recruit 50 women. Which of the following is true? So you see that here, there's a sample size that you have estimated, which is 50 women. There's an alpha, 0.05. There's a beta, which is 20%. And you know that your power in this situation would be 80%. But the effect size here is 20 minutes. So look at the options here. Which one is true? If the minimal difference that would be of concern were 10 minutes, you will need to recruit fewer women. What this question is asked, what this option is saying is that if the effect size that you're interested in was 10 minutes, would you recruit fewer women? No, because we just mentioned that if you had a larger effect size, you have fewer people. But where your effect size you're looking at now is smaller, it means that for you to detect an effect size that's smaller, you would need to have a larger sample size. So you would need to recruit more women if your effect size is actually smaller. So say your alpha now is 0.01. You will need to recruit fewer women. That's option B. No, option B is also wrong because 0.01 is smaller than 0.05. It means that you want much more confidence that you are not making a type 1 error. In that case, you need to recruit more women. If somebody decides that they prefer to use beta is equal to 30, you will need to recruit fewer women. Now, here, it means that they are willing to tolerate a higher level of risk in making a type 2 error. So with higher beta, you need lesser power to do this. So you probably need fewer women to do this. So option C would be the correct option here. Given the time, I'm not sure that we will still until test, yeah.
So I think that so there are a few concepts that we haven't covered, and one of them is confidence interval.
Yes.
The other one is one-tailed versus two-tailed tests, and then the third is clinical and statistical significance. Yes, I agree that it makes sense to skip to this point. I think this is a key point that we should cover. We can cover confidence intervals and the other things in subsequent classes.
Yeah. So in all the conversation that we've been having so far, you would see that what we'll be trying to figure out is that the statistic you have computed from your sample, is that statistic, what is the chance that that statistic actually represents what you have in your population? And we've talked about different kinds of concepts to figure out whether the statistic is close enough. That's where we talked about a p-value. But even if you have a p-value that is smaller than your alpha, what that tells you is that you should have confidence that the relationship you are seeing from your sample actually statistically represents what you would have seen in your population. But what we have seen is that you see many people who conduct studies. When they conduct a study, people are just trying to find a p-value, or they find a p-value that's less than 0.05 or that's less than their alpha. People declare, wow, they find a very great finding. The issue, though, is that something is statistically significant is different from being clinically significant. So you can say, for instance, let's see whether people who are using a new drug, there's a new drug that we're testing. Let's see whether people who are using this drug have lower blood pressure than people who are not using it. So you have people who have blood pressures of 160 over 100, people who have very high blood pressures in your study. And then after you've conducted your study, you find out that when people use these drugs, you do your statistical testing, you find out that you have a p-value that's actually less than 0.05. Voila, you've made a discovery. So you've made a statistically significant discovery. But if the actual difference you find between people who are taking the drugs and people who are not taking the drugs is that it lowers the blood pressure from 160, the systolic blood pressure from 160 to 156, to 157. How much of a difference does that actually make in the lives of the patients that are actually going to be treated? And that's what statistical significance, that's what clinical significance means. Meaning that it is not just that we have found a difference that we know from the statistics that there's actually going to be a difference, but is this difference sufficient to actually have a real meaning for the purpose we need it, for the purpose for which we're actually conducting this study in real life? So, but how do we determine clinical significance? A lot of times, sometimes there are studies already, we know that, okay, what's going to be really significant for this study is if you can lower their blood pressure, not just from 160 to 157, but to something around 140, it will save more lives. Sometimes we know for that. But sometimes we don't really know for a fact. What we have is a convention, a consensus, or we're using our clinical intuition. But the whole essence of this conversation is that we should understand that just getting a p-value that's below your alpha is not the end of the conversation. You also need to think about, well, how does that move the needle in the substantive question we're trying to answer? So I think we're just going to move on from this poll also.
Yeah, so before you go, so one question somebody asked, and maybe this is a question that really goes to
Dr.